I'm getting happy, and I know that you're getting happy because we are moving on to the next section. And the next section is amine. So we want to talk about what an amine group is. Ding, ding. That's going back to Chemistry 251, Orgo 1. That's where we saw that functional group. I'm going to pull that functional group back. We're going to take another look at it, and we're going to talk a little bit about the reactions that can or cannot happen with them. So in this next section, we're going to be focused on the amine groups. All right, so amines, these amine groups can be mean because they're bullies, and they're going to go in and they're going to push most of the other functional groups off of the molecule. And these amine groups are typically NH2s. This is what we saw in Orgo 1. And we talked about how to name an amine, both formally using the IUPAC system and a common way to name amines as well. We really didn't do anything else with them, though. The only thing that we did was name them and identify them, and then we moved on. So here's the thing with amines. They put them in the alcohol groups, just probably because they don't really fit that well anywhere else. And the thing with amine groups, think about the substitution chart. Remember the prettiness chart. The prettiness chart was all about the base, right? Okay, so NH2 down here below, and typically that's how that chart was structured, and they put something like iodine up here at the very top. So the big ugly ones were up here at the top. Nobody wants those ugly ones. That makes a very good leaving group. And then as we made our way down that chart, and you'll see that in the review folders that I've posted for you if you need a copy of that chart. It also can be found in your substitution chapter in your textbook. You would see that NH2 is down below. So I've often called this the Miss America or Mr. America, depending on what gender you prefer. So Miss America or Mr. America would come into the bar and all the molecules stop. They do whatever they're doing. They stop. They pay attention to this NH2 because that NH2 was the most beautiful one of them all. And that leaving group will come in to the molecule and kick out whatever other group is typically there. So in order for an NH2 group, remember, these are reactions of amines. So that means an NH2 group is already on a carbon. It's already on a molecule. So the question here is, if we're going to talk about the reactions of amine groups, what else is out there? I mean, that's how the chart ended. Nothing really was above an NH2 group on that chart. And if you've looked at the template and the model of the reactions that we've talked about, we have either talked about substitution reactions as far as SN1 and S2 goes, and elimination reactions, E2 and E1. Well, Miss America on the chart is very hard to pick off of a molecule. Once you get Mr. or Mrs. America in your house, you're probably going to want to keep them if it's all about the physical attractiveness. And that's all that these molecules care about. They don't care about anything else. No personalities again, right? Molecules don't want that, please. So the substitution reactions, probably not going to happen with amines. The elimination reactions, probably not going to happen with amines. Whenever amines come around, the amines have pKa's of about 36 to 40. They are extremely high. What this means is that the amine group is very, very basic. And very basic means very attractive. Very basic typically means very good nucleophile. And that nucleophile can come in and attack. So if we're looking at reactions of amines, we're going to be limited here, folks. That's the take-home message. We're going to be limited in what we can do because these are so darn pretty. They're so strong. It's going to be hard to substitute these out and to eliminate these out. But we can do reactions with them. Don't take this the wrong way. We can do reactions with them. But compared to alcohols, compared to epoxides, compared to ethers, these are going to be a little bit more stubborn. So you're going to say, well, let's follow the template that the chapter has given us. So it seems like every single time they have wanted us to protonate, bring in an H plus to the system. Allow this H plus to react with whatever type of molecule that it needs to react with. We put it on an OH, it protonated, it left. We put it on an ether group, it protonated, it left. We put it on epoxides, it protonated, it left. So why don't we just protonate the NH2 group? Okay, well, that's a good idea. The problem, though, is that when this NH2 group gains another hydrogen to really give us an NH3 group, the fourth bond is to that carbon. This nitrogen will carry with it a positive charge. However, the pKa of these protonated amines are still around 11 to 15. Oh, they're still basic. They were so pretty that when you take these hydrogens and bam, give it a black eye, they're still pretty. So what can we do with them? How can we get these things to react? This is going to be very difficult, as you can imagine. Even with a black eye, the molecule still thinks that it's one of the most attractive things it's ever seen. I mean, this is how protonation worked. We gave the OH group a black eye, made it ugly, it left. We gave the ether a black eye, made it ugly, it left. The epoxide, it was kind of ugly to begin with, but then we gave it another black eye and made it even uglier, and the ring opened up without a problem. But here with NH2s, it's a whole different ball game. And that's just because they're too darn pretty. That's what these molecules look at. That's how these molecules behave. So even with protonation, we're going to have a hard time doing something with them. So what you're seeing on the screen right now are protonated amines. For the most part, all of these are protonated with the exception of one. And I want you to take a look at the pKa values. Look at the ones up at the top. Protonated amines, they've been given black eyes. They have a positive charge. They should be good leaving groups at this point, right? No. And that's because these were so high of a pKa in the beginning that when you did give it a black eye of a positive charge, it lowered it. Sure, it lowered it. But it only lowered it to 10 and 11 on these three examples. A protonated primary, 10.8. A protonated secondary, 10.9. And a protonated tertiary, 11.1. Folks, they're all super close. It doesn't really matter what kind of carbon they're attached to. So a primary amine is a N group attached to a carbon. A secondary amine is a nitrogen attached to two carbons. And a tertiary amine is a nitrogen attached to three carbons. All of these are fair game, but they're all pKa's of 10s and 11s. Can we get them to react and do stuff? Sure. Yeah, we can do it. But they're going to be much more stubborn than the other groups so far. Down here below, we see protonated amines again in the first two examples. Those are protonated. I see the positive charge. And the reason that these are much lower is because pKa is defined of when it gives off a hydrogen. So if we can convince this molecule that it doesn't need that hydrogen around and make that bond weaker, then we turn this into more of an acid, because by definition that is an acid, proton donor. And when we turn it into an acid, well, my pKa's go down because of that. That's kind of how we define that. So why are these two much lower than the ream up at the top? Well, as you can maybe expect, the answer is going to be delocalization. So when we put an amine group on a delocalized network, like a benzene ring, for instance, this is a double, single, double cause you trouble. So this is a delocalized network and the electrons go all around the ring. Well, double can also be attracted to the positive that's on a neighbor. So delocalization can actually extend on out into the amine group areas and back around into the ring. And this persuades nitrogen that it's wanted. You know, you've got a purpose, you've got a place. We love you, but you know, you don't need that extra hydrogen unless you just really want it. So these hydrogens are more prone to be ripped off. So that way it can leave those electrons that are behind in the bond, and those electrons can now fully participate in delocalization a little bit more freely. So because of that, they are more prone to spit the hydrogen off, which means they're more prone to be acids, which means that their pKa's are much lower. pKa, again, is a ranking of acid and base. That's what we learned in Organic 1, if you had me especially. And that's the same reasoning that's happening here. Same way with this one. It's still delocalization that's playing a factor. If it can get rid of that hydrogen, a set of electrons can now fully participate with the other set of electrons, and this turns into an acid because it's a proton donor. Now, if it's not protonated, as in all of these other examples, look at this tiny little bitty amine. That tiny little bitty amine, methylamine, folks, that's a pKa of 40. Super base. Right there. That's all you need. All right, so what's the issue with the amine reactions? Well, here's one of these examples. They can still undergo things, but we're turning the perspective on something a little bit. It is reactions of amines. And every time that we've used an amine up until this point, we've always had like minus NH2. But this hydrogen can be replaced or added on to another carbon or another alkyl group or whatever the case is. And this is not going to change. So for instance, here we had ethyl bromide. And what we learned in Organic 1 is that the bromo is a very good leaving group. It's real ugly. No one wants bromine. No one wants halogens. That's why they make very good leaving groups. So if this bromine can be kicked to the curb and replaced and substituted with something else, then all of a sudden, folks, we have a reaction that goes on. Okay, well, these are the reactions that we're talking about. So we're not introducing anything new here. So if this bromine can leave, we need something to take its place. Well, this molecule goes into the organic chemistry bar and hangs out and has a good time, and they're there together. And then Miss America walks into the bar, and Miss America comes in, this NH2 group that just so happens to carry with it a methyl. And this compound immediately looks at that NH2 group and says, whoa. That's what I want. So NH2 sees that carbon giving it the eyes. NH2 is going to go in and not waste any time. And NH2 is going to go in and attack that carbon that's partially positive, because the bromine, not only was it ugly, but the only thing that it wanted was money, 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 money. And that was in electrons. So that carbon and bromine says, off you go, don't want you anymore, bye-bye. And what we see is that the nitrogen brings with it the whole party. So not only the NH2 shows up, but the CH3 shows up as well. It's the whole entire molecule. And the reason for this is because nitrogen can hold this positive charge pretty well, because this pKa is still around A10 to 15, 11 to 15, so forth. Not a big issue. It can hold out like this for a while. That's what we're seeing down below as well. Here we have an epoxide. This is an epoxide reaction, but at the same time, cup half full, cup half empty. It's also an amine reaction as well, because we're bringing in an amine. So the same thing happened here. This is going to act as a base. So if the base comes into an epoxide, it's going to look at these two carbon choices and say, hey, oxygen, I've got your back. You know, I'm Miss America. I can do whatever I want to do. And I can pick out whichever one of these carbons that you want me to pick out. And oxygen says, thank God. You're going to take the most unstable, crazy one. That's the one I want to get rid of first. So this NH2CH3 says, okay, well, that's the primary carbon over on the right-hand side. So that's where I'm going to go. And you can take those electrons and basically shove them on up. And then you free up this negative charge. The problem here, though, like we've seen before, this negative charge and this positive charge should not be in the same molecule. They are very close to each other. Both of them are in imbalance. So the oxygen that carries the negative needs a proton. The NH2 that's positive needs to get rid of a proton. And what we see, again, like we saw before, is one of those nitrogens will leave, or hydrogens will leave, and go up here and make that oxygen happy. And that also makes the nitrogen happy and removes the positive charge. All right, so those are two reactions that we have talked about. Neither one of them are new. And folks, that's pretty much it, with the exception of something else. Okay? So these are the reactions. So, surprise, nothing really new has been introduced in this section. Now, before I do introduce the one reaction that we really haven't seen yet based on amines like this, I do want to talk about amine groups and the role that amines typically play, because a lot of people say, well, why do we even talk about these? I mean, if they don't undergo a lot of reactions and these nitrogens are Miss Americas, then what's the importance of them? Well, here's the importance of them. Up here at the top left-hand side, we see an amine group. There's the amine group. That is the structure of cocaine. All right, so cocaine, extraction. That extraction is converted into a compound, and that compound is called cocaine. And this is what we call a lead compound because, folks, believe it or not, cocaine has led us into other compounds that have been very good. So, in other words, a lead compound, and we're focused on an amine group here, plenty of lead compounds that are out there that are not amines, right? This is just one example. But it's a starting place, meaning that we know that we can give cocaine at one time legally to people, almost like a medication. But the issues are the side effects that come along with taking that compound. One, of course, addiction. You need more and more and more of it over time in order to get the same feeling. So we know that there's good things, though, that come along with the use of cocaine, believe it or not. One of these would be something like a painkiller. So how can we take an amine like cocaine and change it into something a little bit more manageable? So hence an improved lead compound. We have to start somewhere. We just don't make this crap up in a laboratory all the time. So now we can take this starting molecule like cocaine that has some benefits associated with it that we would really like to highlight, and we would like to get rid of all of the negative side effects that are associated with that compound as well. So we'll change the chemical structure up a little bit and we'll improve it. And we'll improve it to something that looks like over on the right-hand side, an improved lead compound. And then we have that to start from. Yes, this got better. Not as many bad side effects. We amplified the good things about cocaine that we want it to keep. And then from this point, what we'll do is we'll modify again. And we make things like benzocaine and novocaine and xylocaine. Topicals. We can rub them on our skin. We can rub them on our gums for a toothache. All of these are slight numbing painkillers. and they all were related to cocaine. Why do you think benzocaine is at the end, and novocaine is at the end, and xylocaine is at the end? Where do you think that name came from? It's from a compound like cocaine. So, folks, these illicit drugs that are on the market are just that. They're drugs. And something like aspirin is also a drug. What's the big difference? Methamphetamine, that is a drug. But so is Tylenol. That's a different compound. That's a drug as well. One is sold over the counter, and the other one you can't have. People try to have it. They try to make it in their garage, but it doesn't do them any good. They'll eventually get caught. So what's the big difference? It's the side effects. It's the bad things that happen that if it gets out of control, disaster happens. So can we take something like methamphetamine and can we change it up a little bit in order to make a new compound? And the answer is yeah, it's called Alderol. You ever heard of that one? Give it to kids. What? Yeah, we just changed the stereochemistry of the drug, and that's it. That's all that we do. It's methamphetamine with a different stereochemistry at one location. That's all. And this is okay for a person to prescribe and give. Folks, that's surprising to most people. But this is how the world of drug chemistry sees it. So I know that this is not a full-blown nitrogen reaction, but it does give you a nitrogen-based compound, and it led us to relate that to what we call a lead compound, not a lead compound, a lead compound. I see no lead here, okay? PP, that's PP. I don't see any lead. But a lead compound gives us a place to start. And we take that compound, no matter how bad it might be, and we modify it and we change it into something that's a little bit safer and a little bit more manageable. So while we're talking about the amine structures, I do want to go back and I want to talk about another reaction that is new to you. And this has a special name, kind of like the Swern. This one's going to be called the Hofmann reaction. Okay, so what is a Hofmann reaction? Well, a Hofmann reaction is this concept that amines are pretty stubborn. Very hard to do something with them. So let's say that I have a CH3 group, a CH2 group, a CH2 group, and a nitrogen that's attached maybe to another CH3, CH3, CH3. So there you go. So this nitrogen is going to be a positive charge. And we add something like heat. Can a reaction goes forward? Okay, here we see a molecule. That molecule is an amine. It's a protonated amine. So we know it's not as basic and as pretty as the normal nucleophile would be, but it's still pretty hefty. It's still very attractive. So if we take something like this and we add heat to it, we do get a reaction. And that's what this Hofmann reaction is all about. However, I need another reagent, and that other reagent is typically hydroxide, another base. Why? Well, that's because these two reagents will come together and an elimination reaction is going to happen. And the elimination is actually an E2 mechanism. Once again, Organic One topic. That folder's there for your review. We keep talking about substitution and elimination, and that's why I made that available. But this elimination is going to eliminate something. So what does it actually do? What does it eliminate? Well, without mechanism, let's just look at product. I'll give you the mechanism in just a minute. What happens here, I'm going to redraw my reagent. We'll start there. CH3, CH2, CH2, nitrogen with a CH3 group, a CH3 group, and a CH3 group. So what this reaction does is that it looks at that nitrogen with those 3 carbons on it, right? You see that. And the presence of heat with hydroxide will go in and pew, get rid of that bond. And it eliminates that quaternary nitrogen. We call it quaternary because that nitrogen is bonded to 4 things. When it does that, this nitrogen is no longer positive. It goes back to the original state with 3 groups, and nitrogen is very happy because of that. But this carbon now is missing a bond. There was a bond right here. We just erased it. So this carbon's not very happy. It's shortchanged. So in the Hofmann reaction, what happens is that the neighbor carbon, just so it can make its buddy happy, decides to donate a hydrogen that it has. Just get rid of it. And that opens up a site of attachment that creates an extra bond in between those 2 friends. That's the Hofmann reaction. So the OH is there because something has to take that hydrogen off. And that is the purpose of the hydroxide. So this makes HOH, which is really water. So the Hofmann reaction takes quaternary ammoniums like this and hydroxide with a little bit of heat. You just heat them up, allow these 2 things to react together. That nitrogen-carbon bond breaks. That frees up the nitrogen so it can go do what it wants to do, and it's no longer charged. That carbon shortchanged a bond because of that. And an extra bond forms between the 2 carbons. We form an alkene. Now we can take that alkene and react it with anything else that we want to react it with that we learned back in Orgo 1. Okay, but the problem here is that if you notice what I did, I chose the left-hand side. Why didn't I choose the one up above? Why didn't I choose the one to the right? Why didn't I choose the one to the bottom? Because look at the description that I just gave you. This bond breaks, and the carbon uses its neighbor to stabilize itself with. So that's what gets rid of the hydrogen. Well, if we did that up on the top, this carbon bond is going to break, and that carbon's going to look for a buddy, but that buddy's not there. There's no neighbor. There's no best friend. So that carbon cannot cleave. And the same goes for this one, and the same goes for that one. Those carbons cannot cleave, and that's because there's no neighbor carbon to get the hydrogen away from, so a double bond can form. So this was my only option at this point. So let's talk about the mechanism of this a little bit. I'm going to do CH3, and then CH with a hydrogen that points down like this instead of CH2, because that hydrogen's important. We know it's got to be removed, right? And then a CH2, and then we drew our nitrogen with our 3 methyl groups over here to the side. Okay, so this was what we just used. And we're going to pull in hydroxide. I know that hydroxide has free sets of electrons. Okay, there they are. They're negative. That negative piece is going to be attracted to something that is acidic. Why is this hydrogen acidic? Why does it go there? And the issue here is that this nitrogen is positive. And you know good and well that that positive is going to attract negatives. Okay, well, what's in a molecule that's negative? Electrons. And where are the electrons located? In bonds. So we see almost like a sucking mechanism that happens here. We see electrons gravitate and get pulled in that direction because of that positive nitrogen. So this is what we're going to call alpha, and this is what we call beta. And what happens is that the hydroxide pulls off a beta hydrogen. The beta hydrogen says, okay, bye-bye. And these electrons, carbon takes and shoves them up here to form that double bond that we see get created. And then this carbon says, okay, fine, nitrogen, go away. I don't need you anymore. So all of these things happen at the same time, and that is why this is an E2 elimination mechanism. It all happens at once. So that creates the double bond. When that carbon to nitrogen bond breaks, that frees up the nitrogen piece, so that way it becomes neutral again, and then water is formed as a byproduct. Now, again, the issue, I only had one choice here. There was only one choice for me to pick to cleave that bond. But what if I did not have one choice? What if I had something that looked like this? Oh my God. Look at this structure. Are you crazy? You want me to answer this? Yeah, I do. I want you to answer this. So write down this example. Try to answer it without my explanation. Just use what you know from organic and try to think of a way that you can get a stable, the most stable product out of this reaction. What do you think is going to get formed? Because here the OH is going to do the same thing mechanism-wise. It's going to look at beta hydrogens and it's going to pull a beta hydrogen off, and a double bond is going to get formed, and the nitrogen-containing piece will release. However, what are your options? What are your choices here? So take a stab at it. In the next video, press play. Double check your answer and listen to my reasoning. And maybe, just maybe, you will end up with the right answer. If not, you'll at least know why you made your decision the wrong way, and you can prevent that in the future. I'll see you next.